If you consider this situation, you have pendulums hanging from this flexible beam. If you give a displacement for A, then C will vibrate because C and A have the same length, so they can be a resonance together, while B and D have different lengths, so the frequency for their oscillations is different from the frequency, the natural frequency for A. Okay. So if you have this forced vibration situation, the resonance for A will be picked by C because it shares the same natural length, the same natural frequency. Another situation of great interest is standing waves in air columns. Consider a pipe open at both ends. So here the first harmonic corresponds to this situation. This is 1/2 wavelength. This is 1/4. This is 1/4 together. This corresponds 1/4 plus 1/4 is 1/2. This corresponds to 1/2 wavelength. So L, the length of the pipe, corresponds to 1/2 wavelength, which means the wavelength of the sound wave here, the wavelength is twice L. It's 2L. Again, frequency can be calculated, V divided by lambda. Lambda is 2L, so the fundamental frequency is V divided by 2L. Okay? You see that we have antinode at both ends, antinode, and we have just one node in between. This is the fundamental tune for this pipe. This is how we calculate the wavelength from L and the frequency from lambda. Second harmonic, you will have two nodes. This is second harmonic. Two nodes, and this corresponds to one wavelength. So lambda is equal to L. Therefore, F equals V divided by L, which is twice the fundamental frequency. The third harmonic, we have nodes in the third harmonic, as you can see. Lambda is 2/3 L, and F, the frequency for third harmonic, is 3 times the fundamental frequency. Now, if you close one end of the two ends, you have this situation. The node now is at the closed end. So the first harmonic here, this corresponds to 1/4 of a wavelength. The first harmonic, the wave here, is 1/4 of a wavelength. Therefore, lambda is 4L. Lambda is 4L, and the fundamental frequency is V divided by 4L. Then you can move from first harmonic. This is the third harmonic here. Lambda 3 is 3F1. Okay. The speed of sound experiment, which you were supposed to do in lab 2, makes use of the resonance of sound waves in a tube. It is closed at one end with water. So here you have this situation, the frequency of sound waves from the tuning fork going through the tube. You have this first resonance. First resonance makes this length equal 1/4 lambda. Then the second resonance, when this length is 3/4 of lambda. Then the third resonance, when this length is 5/4 of lambda, and so on and so forth. Usually in this experiment, you start moving the tube down, up and down in water until you hear the sound amplified to check that you have a resonance. So the first resonance corresponds to this. You measure L. L corresponds to 1/4 lambda. From there, you calculate lambda. It's 4L. Once you have lambda and you have the frequency of the tuning fork, multiply them, you get the velocity of sound. A pipe open at both ends resonates at a fundamental frequency if open. When one end is covered and the pipe is again made to resonate, the fundamental frequency is if closed. Which of the following expressions describes how these two resonant frequencies compare? We know that when you close one end, now you have a new resonance for the tube. For the open tube, it is V over 2L. For the closed tube, it is V over 4L. So F closed is 1/2 F open. Balboa Park in San Diego has an outdoor organ. When the air temperature increases, the fundamental frequency of one of the organ pipes, what happens? We are told the thermal expansion of the pipe is negligible, so we don't need to worry about changes in the length due to thermal expansion. We need only to consider the effect of temperature increase on the sound of waves increase. As temperature gets higher, the speed of sound gets higher, and speed is equal to lambda multiplied by F. Okay, so this will result in an increase in the fundamental frequency because lambda will not change. Lambda, like L, we are told L is not going to expand due to temperature changes. Okay, so the change in speed of sound will reflect on a change in frequency. If speed of sound is higher because of temperature, then the frequency is higher.